Yes, sir. I've posted them in the group. Done.
Okay, all right. So let me just take you through what we are trying to do and what this numerical problem is all about, right? Do you remember this linear regression thing, right? What a regression problem is? Uh, when we are trying to predict some continuous variable, right? Based on some set of input features, that is a regression problem. Provided we have some historical data, labeled data available with us, right? We can do that, and that is known as regression problem. For example, predicting the house price given that area of the house, number of bedrooms, whether it's a furnished kitchen, right? Modular kitchen, marble flooring, and other aspects. These are the set of input features that we have. And output that we have is the house price, right? So what we typically do in linear regression is let's say we are given a data set of 1 lakh records. I will divide it into training and test set. So let's say 70-30 is the split. 70% of the records I'll use for training, maybe 70,000 in that case, and 30% I'll use for testing. So when I'll do so, I will have a input features using which model will learn some equation, and then I will give the input features of the test data for prediction. I already have the actual output, but for prediction, I will give it and then I'll compare it. How much is the difference between the actual output and the predicted output, right? And that is what we call as an error, right? That is what we call as an error. For one particular problem statement, there could be multiple regression models. Uh, the model which gives this particular error as minimum, that is the model we are interested in, right? In general way, I can say that model which will give me the minimum error, that is the model I am interested in. Did you get some context? I cannot write today, so I am also feeling like how should I take a class, but are you able to relate it what I've said?
Yes, sir.
Yeah.
So, so basically, you said that in basically the linear regression, we take a set of inputs and then we predict another variable using those. And the function that we use to verify it against the test data, which gives us the error, see the difference between the prediction and the test data.
Hmm.
That is the function that we are interested in, correct?
Yeah. So uh, the function which we represent in the form of error is its predicted versus actual output, right?
Got it.
So how do I represent my data, right? Whatever x you are seeing right here, that is input feature. So what in the first record, now you see here what is mentioned here, x1 raised 1, right? x1 I, then x1 n. What is it? These are the records which I have. For the first row, what is the x1 feature? X1 feature may be the area of the house. Then x12 could be, oh sorry, x21 could be the next one in the same row. uh, it could be, let's say, proximity to the schools or the nearby market, right? Third could be any other, whether it's there's a modular kitchen or not, whether it's a double floor or single floor, could be n number. So d features are there. From 1 to d, we have d features. First row represents the first record, second row represents the second record, third row represents the third record, and so on. Does that make sense?
Yes, sir.
Does that make sense? Then what we are interested in finding out weights, theta 0, theta 1, theta 2, up to theta d. Now what are these weights? Each feature, how much it influences the output. Maybe the area of house could be one of the major. So theta 1 might represent that, theta 2 might represent the represent some other, maybe whether there's a marble flooring or not, number of bedrooms and so on. So there, if there are d features, each of them will influence in a certain way. So we have d weights with us, represented from theta 1 to theta d, and theta 0 is the bias, right? Bias term. That if you remember linear regression, right? Straight line. I said theta 0 plus theta 1 x. Correct? In my earlier sessions, if there is a straight line fit, right, that is theta 0 plus theta 1 x. Now, what is theta 0? What is theta 1 x? Here, I am also not able to write even. I don't know what is the issue. Even with the, I think using this mouse also, I'm not able to select a pen even. Okay. What is the equation of a straight line? Theta 0 plus theta 1 x. Okay, let me open a Word document also.
Sir, actually, the PPT is not in editable form. That's why you're not able to write. So if you will enable editing, then you will be able to write.
That's one issue I can also see right now. But even I'll not be able to write those geometric terms, right?
Yeah, yeah.
Let me change it to editable form. So it's very difficult to write, right? See. Okay, let me use the word format. I'll keep on switching between these two. Okay, so let me write in a simple way. Y is equal to mx plus c. This is the kind of equation that we use in linear regression, right? Where we said that, okay, m is the slope, x is the input feature, c is the bias term, right? Let me. So now, when you see machine learning books, right, they use the terminology theta 0, theta 1 or W0, W1. So basically, what is your W0? W0 is C, right? And M is your W1. Theta 0 is this, theta 1 is this. Make sense? I will not be able to write theta 0, theta 1 here as such. I have to use equation editor only, then I will be able to write. So that's why I've written y is equal to mx plus c. Now, what we identify using linear regression is M and C, simple linear regression if I talk about, right? So one of the models could be, let's say 2 plus 3x. So what is my C here? What is my C? You have to give an answer.
2.
2. What is M?
3.
3, right? So our job is to predict these two, right? So in machine learning terminology, we name it as theta 0, theta 1. This is theta 0. I'm writing, right? This is theta 1. Make sense? That's a simple linear regression model where one input feature is there. Let's say area of the house. Basis that only I am predicting, right? But in reality, we've got multiple features. So that slide is showing you the generic equation, right? So this is the data set completely which we have. This portion, right, is complete data set x1, x1 raised to x1 1, right? Then x1 I, then x7, x1 n. So n records are there within me. I have d features. So in simplistic case, d is 1, right? So I'll have only two weights, theta 0 and theta 1. If I have d features, I'll have d plus 1 weights, right? 1 corresponding to each feature and theta 0 for the bias term. Make sense?
Yes, sir.
Yeah. So this is how I represent it. This is in the form of a matrix, right? So this is how it is written, h theta x, right? Basically the predictions. Now from the data set, we have to learn these parameters, which are weights of each of the features, correct? So from an exam perspective, I'll not give you a very comprehensive problem where you have to find out multiple thetas. Maybe a simple linear regression problem may come, right? Look at this. Okay, I'll come to this later on. one method, right, which we discussed was a gradient descent method. So our objective is to find out theta 0, theta 1, right? So what this typically says, you initialize theta 0, theta 1 at any point, right? At any point. So why this curve is there? Very first thing is why this curve is there, all right? Why it's not something else? The error function which we take, right, which I said predicted minus actual scare, right? Normally, how we calculate the cost function? Predicted minus actual scare. If it is mentioned somewhere, let me see. It is mentioned here, right? Y cap, Y hat is the predicted, Yn is the actual. This is summation 1 to n for all the points, right? 1 by 2n. This is my cost function. Cost function in a sense, error function. This error function, when you represent it, it comes in the form of this curve, right? When you plot it for different values, it will come in this form of a bowl shaped curve. So it has only one minima point, which is denoted by this yellow line. So our objective is to find out this minima, right? Because my objective is to minimize this error function. Now you see the things which you have studied, right? Finding out minima, finding out maxima in mathematics, right? Using differentiations and all. Now that is applicable here. That is applicable in real life scenario. Is it making sense?
Yes, sir.
Yes, sir.
So you can start with any theta. So what the blue point is saying is this theta you can start. Move it over iterations and see if the cost function is improving. Improving means the cost is decreasing, the error is decreasing. So we will keep on moving towards this, and slowly the algorithm will converge to this theta. Slowly algorithm will converge to this particular theta, right? So what is the value of theta 0, theta 1 at this point? That is what we are interested in, right? Now let us look at this. I'll come to this hyperparameter later on, right? Look at this function, right? So this method which I was telling, this is known as gradient descent method. You start with any theta 0, theta 1, gradually move towards the minima. If you see this kind of a function, do you see any challenge with this? Challenge, let me explain it, okay, right? This is a curve, right? So there are some minima points coming in. If you look at this, this is one minima, right? If you look at this, this is global minima, right? In this particular function, this is the lowest point. Objective is to find out this lowest point, right? But using gradient descent, what may happen is I have started at this point. I know I have to go towards reduced cost. I will come here. The moment I'll reach here, if I move further, the cost will start increasing in the other direction. Yes or no? Because I am
Yes, sir.
moving away from this minima, then the algorithm will say, no, I am going in the adverse direction. Again, it will come back and try to converge, right? So it will stuck in this local minima. This is local minima for this particular curve, right? Half of the curve. This is not the global minima. This is also, but this portion is global minima. So how to reach this global minima? So that is a drawback of gradient descent algorithm, that you can reach to a local minima, you can converge to a local minima, while the global minima can exist somewhere else. So that is a pitfall of a gradient descent algorithm in simple terms, right? Does that make sense?
Yes, sir.
Is it making sense to everybody, please? Vasu, Ali, who all
Yes,
have
sir.
joined,
Makes sense.
Yes, sir.
Shweta and Suchitra, right? Keep responding. Look at this cost function, right? So what is the point of minima? This is 3D now. 3D, this is again a bowl shaped kind of a thing, because there is one global minima somewhere here where there the arrow is mentioned, and these are the values. right? So we are interested in finding these values, right? So this is the method how to update our thetas. This is the method how to update our theta. Theta j is equal to theta j minus alpha times partial derivative of this with respect to that cost function. You know partial derivatives? You remember? You know how to take a derivative?
Yes, sir.
Okay, if y is equal to 2x, if I write dy by dx, what it will be?
2, sir.
2, right? Simple thing. So we have to take with respect to this theta which we are updating, right? Don't look at the complex thing which you might be feeling a little scary that what is there in the down, right? But just remember this part. Now, I'll go back. We are given a data set, right? I'll take simple data set example and then I'll show you 1 or 2 iterations how to update it. Look at this portion. Okay, this is solved using some different method. Let me see. Yeah, here it is. Consider the following training data. What is the training data available with me? I have one feature X, right? And the output feature Y. So 2 records I am taking X1, Y2, X3, Y4. Maybe it is the area of the house, Y is the price of the house, let's say. Very simple data set with one input feature and one output feature. Make sense? How many weights will be there if I have one input feature? How many weights? How many thetas will be there?
2.
2, right? Theta 0 and theta 1, because it's a simple linear regression now. Now you see, we started with any random values of theta 0, theta 1. Theta 0 is 0, theta 1 is 1. Can you see that?
Yes.
Right. So what is my function, predicted function? Y is equal to 0 plus 1x. Theta 0 plus theta 1x. This becomes 0 plus 1x.
Yes.
So what is the cost function?
Sir, sorry. Why we are taking C as 0? I didn't got that.
Why we taking C as any random value you can take?
Okay. For simplicity, we are taking it 0.
Yeah, it's any random value. You want to give it some value, theta 0 also you want to take it 2, you take it. Not an issue.
Okay.
Ultimately it will converge. Some random values we have taken. You can try it, right? Unless and until sometimes it is in the question, it could be mentioned. You start with this theta 0 and theta 1. Then you have to start with that. But if it's not mentioned, any random values of theta 0, theta 1 can be taken. Generally, right? In deep learning and all, you will see to optimize these randomization values also, because what will happen is if you start with some different random value, the number of steps or the iterations it will take to converge can be different, right? So our objective is to minimize that also to in order to reduce the computation cost. Okay, that I'll come to it later. Yes, Ali, go ahead.
Sir, I just wanted to ask that as we saw the drawback of this, right? That if we take any random values of theta 0, theta 1, we may end up in a situation where we get stuck in the local minima, right? And
No,
that will take a lot of.
no, the statement you are making is little bit incorrect. Let me modify the statement. It's not about that theta 0, theta 1 values, random values decide whether it is going to stuck in a local minima or not. It's the nature of the function which decides.
Okay. So
Or
if we take
maybe I think I got your point. What you are thinking is, let me come back to this slide. You might be thinking, if I initialize theta 0 here somewhere, right?
yeah,
Rather than here, probably I'll converge to a global minima. But if it is random, I'll converge to a local minima, right?
Yeah, and what if like the earlier minima was global and we started later, then we may end up in local itself, right? We will not go to
Yeah.
the global itself.
That's a general thing with the gradient descent, right? So
Yeah.
you may find a global maxima, a global minima, or you may not find, right?
Yes.
Right. So
So
this
in
function is like this. Imagine if it is a sine wave kind of a curve, and right, there are so many peaks and so many bottoms.
so sir, like when we solve problems, and in that time when we let's say assume random values, and
Hmm.
when we come to the answer, we get stuck. So in a local minima. So then will that be fine, or how do we like? Is there any value that we should consider to avoid the situation, or this will happen nonetheless of whatever we
No,
choose?
with gradient descent, this is likely to happen, that you may end up in converging to a local minima. If the function has multiple, you may find out a global minima, but you may also end up in a local minima. Both cases are possible. You want to find out global minima, there are other optimization things that we need to consider, right?
But thank you.
So this is the numerical problem. Simply when we have a bowl shaped function where there is one global minima, then we are using gradient descent. Make sense?
Yes, sir. Next.
Okay. Now coming to this, I have initialized any theta 0 and any theta 1. Right. So y is equal to 0 plus 1x is my now function. Right. This is what my weights are. My cost function now. 1 by 2n y cap. Y cap is predicted values minus y square actual values. Actual values are 2 and 4. Predicted values. I'll plug in the value first 1. And what is my predicted value? 0 plus 1 into 1, 1. Second time I'll plug in 3. So 0 plus 1 into 3 will be 3. So you look at it, theta 0 plus theta 1 x minus 2 square. So this is actual 2, then this is actual 4. So first time I plug in 1, second time I plugged in 3. So I have to square it. So 1 minus 2 is minus 1, but I have to take a square, so it will become plus 1. 3 minus 4, again it will become plus 1. So 1 plus 1 is 2. Outside it is 1 by 4. So you remember our cost function 1 by 2n. N is 2 here because I'm taking 2 points in the data set just to explain you, right, how the things actually work. So 1 by 4 multiplied with 2 is 1 by 2. So now you see my cost function has a value of 1 by 2 at this theta 0 and theta 1. Cost function error function is 0.5. It is showing me 0.5 value. Make sense? Till this point, we have done nothing, no updations to theta 0, theta 1. We initialized some value of theta 0, theta 1. We plugged in the numbers within the cost function. Using the data set, we figured it out what is the value of the cost function. Make sense?
Yes, sir.
Predicted minus actual scale. So now you have randomly thought of, okay, this is my predicted values and this is what I have got as a cost function. I want to now update it, right? Let us see that portion. Theta 0 is equal to theta 0 minus eta times partial derivative of theta 0. Partial derivative of cost function with respect to theta 0. Right. Now, if you look at it, I want to do partial derivative of the cost function with respect to theta 0. Cost function is y minus y cap minus y square, right? So theta 0 plus theta 1 x minus 2, theta 0 plus theta 1 x minus 4, right? So that is with respect to the data point. You see, this is my cost function, right? So if you look at it, if I have to do the partial derivative, now you see it was a square, so it will come in the front, right? That is how you take derivatives. And with respect to theta 0, this term will be treated as constant, theta 1 x. Theta 1 x will be treated as constant because I am going to do partial derivative with respect to theta 0. And when I'll do for theta 0, it will become 1. So that is what it is mentioned. This theta 0 will become 1, right? This term constant, so it will become 0. So this has turned out to be 1 minus 2. Similarly, it will turn out to be just a minute. Yeah, so theta 0 plus theta 1x, the when you do a partial derivative of this, right? So this is what you have got, and you just need to plug in the numbers. Just a minute, there's some message. Apparently, I'm doing, I'm on a, I mean, I've been given some other responsibility, so I'm just looking at that. Sorry for that, right? So let's look at it once again. Theta 0 is equal to theta 0 minus eta times partial derivative of theta 0. Okay, first thing that you do is just compute this term. What is the cost function? This is in front of you, right? Use this cost function, this one. Theta 0 plus theta 1x minus 2 square, theta 0 plus theta 1x minus 4 square. This is my cost function. Now you do a partial derivative with respect to theta 0. How will you do this? If you do this, right, this will come, this 2 will come in front, right? It is kind of x square. Yes or no?
Yes, sir.
And if you do the derivative of this, what, okay, if you have
So your,
x,
so your cursor isn't moving, I think.
Yes, sir.
what
I
happened?
don't know if it, your
What
cursor
happened?
isn't moving, sir.
Cursor is not moving. Okay,
Yeah. Now it's
let me highlight that portion, right?
done.
Okay, if you want to take the derivative of this, right, it's kind of, let's say y is equal to x square. Now you are doing dy by dx. So what will happen? 2x, right? That is what is being happening here. Or let us say if it is x plus 2 square, x plus, or yeah, x plus 2 square, right? How will you how will you take the dy over dx derivative? X plus 2 square. You will write 2 into x plus 2 multiplied with derivative of x plus 2,
2x plus 1.
right?
Yes, sir. Using the chain rule.
Using the chain rule, correct? Same thing is happening here. Now theta 0 is kind of my x, right? This is constant because I'm taking derivative with respect to theta 0. This is my constant thing. So this will just come from the front, and whole of this thing, when you divide, when you take, um, you have x, right? You take dy over dx, that is 1. So this is what we are taking it as 1. This whole term will turn out to be 0. So simple thing that comes up is 2 multiplied with this, here also 2 multiplied with this. And now you plug in those numbers, that theta 0 plus theta 1x, right? So 2 multiplied with this is 1 minus 2, right? Because theta 0 is 0 and this is 1. So 1 into 1 is 1, 1 minus 2, right? 2. Then this is 1 into 3, 3 minus 4 is this much, right? Now you multiply this, this turns out to be minus 1. The derivative of this turns out to be minus 1. And now how do you update your theta 0? Theta 0 has to be updated. Theta 0 is equal to theta 0 minus, this is some hyperparameter, right, which is known as learning rate. I'll come to this later. You put this value here and that this learning rate be 0.01, and then you put it minus 1, so 0.01. So from theta is equal to 0, it has moved to 0.01. A small movement has happened. smaller movement has happened, right? Is this first portion clear or not? Yes or no? Should I assume that it is not clear? Anish,
At the end, can you explain
which one?
Eta.
after the last, yeah, this one? What happened over
Okay,
here?
this is clear how to calculate this partial derivative and come up with a value of -1. Is this fine? Is this part fine?
Yes, sir. We just applied derivative rule and then we got this answer.
Then we are taking n value as 2 because we are doing two equation.
Anish, your voice is not very clear. Can you be more closer
Sorry,
to the
sir.
mic? Yeah.
So this we are taking the value of n as 2 because we are taking two values for this equation. 1 by 4 I'm asking about.
No. These are the two points in the data set, right?
Okay.
Only
So if
two
we
rows
take
we
3
have.
points, then we will put n equals to 3.
Right.
If we are given with 3 points in exam.
Yes. And then
Okay,
this
okay, sir.
equation will also expand, right? Right now you have 2, then you will have a third bracket also, right?
Yes, sir.
Because
Yes.
theta 0, theta 1 x, let's say it is next is 5 and 6. So x is 5, y is 6, so you will expand it again, right? 5 minus
Yeah.
6 here it will come out, right?
Okay, sir.
So this -1, right? How to update this? This is the way to update it, right? I have shown you earlier also how to update the weight. Look at this. So alpha or eta, whatever you want to write it, it's a learning rate basically, anything. So this is a way to update. I'm updating theta 0, right? So I'm taking partial derivative with respect to theta 0, right? Make sense? This eta value, which you are thinking how this 0.01 has come, right? It will be given.
Okay, sir.
This will be given, but it depends on like how to decide this. If I have to talk with practically, right? We have to experiment with it a little bit, right? Depending on how fast we want to learn or how slow we want to learn, right? I'll let you know. Imagine, okay, let me, where you are confused first, let me know that. Anish, Ali, Vasu, where you are confused? Are you okay with the partial derivative term?
Yes, sir.
Yes, sir. I
Where,
just had confusion that how 0.01 came suddenly.
okay,
That
that
is it.
value will be given to you. Okay. What is it? I'll explain it, right? Imagine this is 0.1. So what will be the final value of theta 0?
0.1.
0.1. Imagine if it is 1, it will be 1, right?
Yes,
So
sir.
depending on its value, if it is smaller, the weight updation is small. If it is larger, the weight updation is larger. Generally, this value is between 0 to 1, right? Generally, this value is between 0 to 1. And for exam purpose, it will be given. If it is not given, you assume any value between 0 to 1 and solve it, right? Now, why this is important is, look at this. I have started at this point, right? If I keep alpha small, right? So I may be coming this much smaller steps, right? You see here. If I keep it large, maybe my step size will be larger because from here I'll directly reach here, from here I'll directly reach here. So still if it is larger, what will happen is I may miss this point and I'll directly oscillate towards that. And maybe while coming back again, I'll come back here because my alpha is larger. If it is too small, I'm taking too many steps to reach at this place. If it is too large, I may oscillate between these 2 points and never converge to this particular area. So this alpha value has to be chosen carefully so that we converge, right, to a global minima. Too small alpha results in increase in the competition cost. Too large will keep you oscillating between this and this, and you will not end up in reaching a global minimum. Make sense? What is alpha or what is eta value?
Yes, sir.
From visual diagram, now it is making sense. Yeah. Okay, now this is only one part that is computed theta 0. We have to also update theta 1. How to do that? Now let's look at theta 1. Now my partial derivative with respect to theta 1. If I take the partial derivative with respect to theta 1 of this term, now theta 1 is this, right? Now this will be treated as a constant. So obviously this 2 will come forward, but from this particular term also there will be one value that will come as, that is x. Look at this, x, right? So if you take derivative of 2x, it results in 2, right? Now it is theta 1x. Theta 1 is my derivative with respect to, the term with which I am taking the derivative. So my result will be x. So this is multiplied with x. Whole term is multiplied with x. Chain rule, remember?
Yes, sir.
Exactly that. Partial derivative with respect to theta 1 results in this x. Now you plug in those numbers again, right? Simple numbers again, and you get a value of, you see here as -2, right? -2 of this particular derivative. Now you want to update what? W1. 1 minus W1 value was 1, right? Theta 1 value was 1. 1 minus 0.01 multiplied with -2 eta times, right? This is the only equation that we are using. Instead of theta 0, we are using the partial derivative with respect to theta 1, which we have calculated. So it turned out to be 1.02. So next weights which we have got after first iteration is 0.01 plus 1.02x. Make sense?
Yes, sir.
So maybe this is my first step. If I go back to this term, right, this particular thing, I have reached from this point to this point. In the next iteration, again, I'll update, I'll reach from this point to this point, and so on, right? This is what is happening. So this is first iteration, right? Now, second iteration, you will have to use these two values. You don't have to use 0 and 1, right, which we started initially. In the next, for the next iteration, you will use these. So this is the computation of cost function. So you remember our cost function was having a value of 0.5 initially, 1 by 2. Now it reduced to 0.45. So it means it has improved also. It has improved. Make sense?
Sir, can you just repeat how did you get x in the first equation itself?
This portion.
Yes.
Okay.
Is it what we are assuming or?
No, not assuming. It's a derivative thing.
So, like once we got that answer earlier, then what did we derive again?
I didn't get you. Come again.
We got 0.01 as theta 0, right?
0.01 as?
Theta 0 earlier before this.
See, eta is given to you. We are not deriving eta here. We are
No, I
finding
said
out. We are finding out the weight updations. Yeah. Ask,
no,
please. Go ahead.
yeah, I'm saying in the previous slide before this. Yeah, this we got right 0.01 as theta 0. After this, how did we get that equation? On the next slide.
Which equation? This one.
This one, yes.
So what is our cost function? This portion, right?
Yes.
This is our cost function. If I take partial derivative of this with respect to theta 0, I am getting this, right? If I take partial derivative with respect to theta 1, I am getting this.
Okay, so now we took with respect to theta 1. Then.
Theta 1.
Okay.
You remember, this is our generic updation. Theta j. First 0, then 1, then 2, then 3, and we are taking up to 2 only to make it simple, right?
Okay.
We are considering only 2 weight updates.
Okay,
This
got it.
x which you are getting right, this is a derivative concept.
Because of that, okay.
Yeah. Okay,
Sir,
let's
in
say
this W1, in this
let's say
W1, where this,
yeah, W1 is
yes, sir, why we are taking this value as 1 minus, where is this 1 coming from? Can you tell again?
where this 1 coming from, this portion, right? 1 is the value
Yes.
which we initialized. Theta 1 was 1, right? So
Okay,
W1 theta 1, consider it as same. Here it we used 0, you see here, because initial value of theta 0 was 0.
okay, sir, got it.
So you take derivative of x square plus 2x. Okay, yeah, x square plus 2x. Take x square plus 2x whole square. Take derivative of this. X square plus 2x whole square. What will be the derivative of this? X square plus 2x whole square. Dy over dx. Ali, what will be the derivative? Very simple. Mathematics.
2x plus
2 in 2
2.
into x square plus 2x multiplied with derivative of x square plus 2x, right?
Yes.
You can learn this. I mean, if you are forgetting this portion, right, how to take derivatives, you can just revise that part and then come to this partial derivative thing, right? Then you will come to know why this x is written. So you have to take the derivative of this with respect to theta 1. When you take with respect to theta 1, you have x term here. So if there is a function like y is equal to 2x, you take derivative of that dy over dx is 2. Now I am taking dy over d theta 1. It will be x only, right? That kind of thing I am doing here. So 2 multiplied with this, multiplied with derivative of this theta 0 plus theta 1x, which is x in case of theta 1. Because this term is considered constant. This is partial derivative now. Now you are realizing the importance of derivatives practically where they are being used.
Yes, sir.
Can you do one more thing? Now you will have to solve for next iteration. So you have the weights now 0.01. Write it down. Theta 0 as 0.01 and theta 1 as 1.02. Right? Now use these two equations again, right? And use the same data set 1, 2, 3, 4. For the next iteration, you solve it.
We got it, theta 0, 0.01, and theta 1 is
Theta 1 is 1.02.
1.0. Okay, sir.
So you have equation like 0.01 plus 1.02 x. Now for the next iteration, you have to find, right? Keep alpha as eta or alpha 1.01. I'll give you 2-3 minutes, right? You do it. I'll wait for your answers to be uploaded, right? Do it this much step by step. Hello. Solving?
Yes, sir. Yes.
Okay. So only change that you will have to do is whatever theta 0 you were taking initially as 0, you will take it as 0.01 plus 1.02 into 1. So 0.01 plus 1.02, it will be 1.03. 1.03 minus 2. This will be 0.01 plus 1.02 into 3. 1.02 into 3 will be somewhere around 3.06, right? 3.06 plus 0.01 will be 3.07. Then you subtract minus 4 and then go around with the things. So instead of 3 minus 4, you will have some 3.07. Here you will have 1.03. And then you see what is the value that you are getting for partial derivative of theta 0. Are you getting my
Sir, I,
point?
yes, sir. I got theta 0, sir. It's
You got theta. Okay. What is the partial derivative you have got with respect to theta 0 first?
minus 0.02.
Minus
02.
0.02. So you have got around, see, if I do it, if that is 1.03 minus 2, it's 0.97. 0.97 into 2, right? So first term.
It's minus 0.97. It would be.
Yeah, minus 0.97, correct.
Yes, sir. And the second
0.9.
bracket calculation will be minus 0.93.
Yes. So minus 1.94 for the first term, right? Instead of 2. And you said 3.93. What will be the second term?
Then after
Which-
the whole, okay.
3 minus 4. In place of 3 minus 4, what will be the second term?
Then it will be 0.01 plus 3.06
Minus 4.
minus 4, correct?
3.0. So it is 0.93, right? Minus 0.93.
Minus 0.93, correct.
So minus 0.93 into 2. Right? So 1.86. So this will be minus 1.86. This is whatever earlier we have found out, right? Then add it, right? Then subtract it by 4. So, oh, sorry, divide it by 4, and that's what the result is. So this was 1.03, right? 0.97 into 0.97. Sorry, 0.97 into 2. So
So we can
1.9.
take the 2 common and make it 1 by 2 in the front. I
That
did
is
that.
also possible. That's also
Yeah,
fine.
yeah.
So 3.8 divided by 4 you are getting ultimately minus 0.95. What is the final result?
1 second, sir. So this bracket will come as minus 1.9 and after dividing it by 2, it will get 0.95 minus.
So what is the total final value of this partial derivative with respect to theta 0?
It is minus 0.95.
Minus 0.95, right? That's what.
Yes,
Yeah,
sir.
fine. That's fine. And then you can plug in these numbers, right? So 0.01 was the value, right? Initial value instead of 0. 0.01
Yes, sir.
multiplied with minus 0.95. So what you will get? 0.095. This value will turn out to be 0.095. This is 0.01. Point 0.01 plus 0.095. So it will be 0.195. Yes or no? Anish, how
Sorry,
about
sir.
what is final value of theta 0? Plug in the numbers.
Yes, sir. For me, it is coming 0.92.
0.92. How? You got 0.95 as the value, right? From partial derivative.
So minus
Min
0.95.
minus 0.95. So in
Yes, sir.
place of 1, I'm putting minus 0.95.
Yes, sir.
Minus 0.95 will change to, it is multiplied with 0.01, right? What will be the value? 0.095?
Yes, sir.
0.095 plus 0.01.
Sorry, sir. I took the value of theta different. That's what's
Anyway, you got the idea, right? How to do it.
Yes, sir.
Calculations, these are very simple calculations, mathematics, right? So you can use calculator and compute it even, right? So you got an idea how to update the weight. Similarly, you can update theta 1 also, right? Others, Shweta, Vasu, Ali, Suchitra, are you getting?
Yes, sir, I'm trying to follow.
Okay, right. So this is one way, right? So maybe this, then you can find out the cost function, right? So at least practice 2-3 iterations of it, and this will help you out how the things have to be worked out, right? Now there are questions on maybe you see this part, right? What is happening is impact of learning rate. If it is kept 0.02, slowly it is coming to this point. You want to fit this, right? We have started with this line, any random theta 0, theta 1, right? And gradually it is coming to closer to these set of points with this alpha. But when alpha is 0.1, see with these many things, right? It has come very closer to these points which it is fitting it. 0.5, very high alpha. Started here, jumped over this, right? Which I told you. It has missed the optimum value here and jumped to the other side. So that is what this large value of alpha is denoting, right? So we have to be careful while choosing alpha. But for exam purpose, don't worry, it will be given, or you can choose any value between 0 to 1 if it is not given. But practical understanding you should have. If I am trying to fit a straight line, I am starting with any random line of theta 0, theta 1, slowly updating. So those lines are coming, right? I am going closer to the points, and finally it will converge at some point. But if it is very large theta, from here I am directly jumping to the other side, right? That's the problem. Now further, what's the challenge with this gradient descent algorithm is the computation cost. You see, we have taken 2 records, right? And on basis 2 records, we are updating. But how many records do we generally have when we are building a machine learning model? Maybe I might have 10 million records. So for each weight updation, right, I have to use 10 million records. Imagine if there are 100 weights to update. 100 into 10 million. See the number of computations required. Are you getting my point? We updated theta 0, we used both the records. We updated theta 1, we used both the records. Now I'm saying those records will be in a 10 lakh or 1 million, 1 million or 10 million records will be there. And then further, right, how many thetas will be there? That's another challenge. Now, how many iterations will we are spending to converge? If there are 1000 iterations I'm spending, right, to converge from 10 lakh records, 10 lakh into 1000, imagine the number of computations that we are running. And that is why you see for ML and DL things, they say, okay, we want to go with GPU based systems. You must have heard about this GPU based systems.
Yes, sir.
Right? But let's say I am working for a client and client say I am okay with 10% error. So I need not to go to this global minima. If I am coming to some point, let's say where the customer says, okay, I am fine with 10% error. Maybe I am reaching at a yellow point, right? At this point, if I am getting some 10% error, 2 iterations or maybe some few iterations earlier, I am getting some 10% error, I may stop here because my customer is satisfied. From here to here, maybe there are lakhs of iterations running and it will incur a huge computational cost. So it depends, right? What we want also. Global minima lies at the center, right? But if customer says you are a client and the customer says, okay, I'm okay with 10% error, why you would incur extra cost of computation otherwise, right? It comes with a cost. Computations come with a cost. I hope this makes sense of how to update weights using gradient descent.
Sir?
Yeah, please go ahead.
Sir, how do we know that we are at the global minimum? Like we do a lot of iteration and the value saturates, so we come to know, or is there any other method that we
Yeah,
are at local minimum or global minimum?
there are things, right? One is uh, how do we basically you're saying how we come to know that we have converged, right?
Yeah, sir,
Maybe
it's global minimum.
yeah, maybe when I update the weights beyond this, right, the cost will start increasing. If I update the weights beyond this, the cost will start increasing because at every theta 0, theta 1, I am calculating some cost. I want to reduce that cost. The moment it start increasing from the previous iteration, it means I have started diverging again. Make sense?
But then, sir, that could
It
also
will be in the
happen in
case of
case of a
local
local
minimum also.
minima, right?
Yeah,
It
sir.
is the case of, come again,
Like
please.
the value will increase if it is a local minima as well, right? Like let's say we get a value and that is a
So
local minima, then the
that's
next value will
fine.
increase. No?
You are talking about some different function, not a bowl shaped function, right? Which has only one global minima,
Yes,
one
yes.
minima, which is the global minima. For those, right, we have some other sophisticated things, and that it's always a challenging problem to locate the global best solution, right? When you have very different sets of functions. So there is a whole field of meta heuristic optimization, if you want to learn about it, where they talk about optimization of more complex functions than this. Here, we need not to go to that particular level when we have that kind of a function, because linear regression we are dealing with, it always gives me a bowl shaped function, that error function. So I need not to worry much about that. If I have some very complex function, cost function, right, then obviously we have to do some meta heuristic things in that case. Your challenge is like in this function, right, not in the other function, which is bowl shaped. So you want to know whether you are at a global minima or not. You may be at local minima. You might have intuition I am at a global minima, but actually you are at local minima. How do I ensure that I am at global minima with respect to these kinds of functions which have multiple bottoms, right? That is your question, right?
Yes.
Yeah.
Yes, sir.
So for these things, see, one thing is there's not, I believe there's not foolproof technique that we can always reach the global best solution, right? So it's all finding out the best among what we have right now with us, right? So for that, we have some other optimization problems, other optimization techniques, right? So it's all complex mathematics behind this. But it's good that you are asking questions. You have some curiosity now, what is going on. Be regular in the classes and ask such questions. So there is a field of meta heuristic optimization, right? Which you can want to read about it, you can read about it, right? We can discuss a bit on this, provided if you come up with the questions. Otherwise, it will be very, very complex if I start doing that part. Okay, so this is one. This is another form of solution that we can come up with, right? Theta 0 and theta 1. That is known as a closed form solution, which is done using matrices, right? Earlier, I was saying I can represent my weights as this and data set as this, right? And this is my prediction function there. H of x is my prediction function. Okay, solve for optimal theta analytically, least square based solution. Notice that the solution is when this particular value is 0, right? That is a solution I am interested in. What is j theta? J theta is my cost function. When that value will turn out to be 0, right? 0 means that kind of a minimum value that we are interested in. You remember, if you have to find out minima, you take the first derivative, equate it to 0, and then you find out the points. Okay, at this point, the function has a local minimum. Do you remember that? This is mathematical thing covered in
Yes, sir.
mathematics. Same thing they are doing here, right? They have j theta like this. Now they are differently representing it. X theta, basically this portion, right? Ultimately, how I'm predicting the weight? Theta 0 plus theta 1 x. So theta 1 x1, if there are more weights, more variables, theta 2 x2, theta 3 x3, and so on. This is the summation, right? So that is what they are doing. And they are representing this in this form, x theta, right? X theta is my predicted, this is my actual. And if they want to take this j theta, right? So they are taking a transpose of this multiplied with x theta minus y. This is the form of another closed form solution. And ultimately, if you want to find out all the thetas in one go, right, you can use this equation. You can use this kind of equation. X transpose, what is X? This matrix. X is this all input matrix, right? This matrix is X. Transpose, you know how to find out transpose. Multiplied with X. Then taking the inverse of this. Then X transpose Y. So you multiply all these things, you will get your optimal value of thetas in one go. But finding out inverse is a very challenging problem in mathematics. And imagine if you have 1 lakh records or 10 lakh records and you are trying to find out the inverse, how computational intensive it could be. You know how to find out inverse of a matrix? You need to go with the minors.
Yes, sir. Minus cofactors and everything.
Yeah, minus cofactors, right? Imagine you have 1 lakh records here. Generally, we are used to find 3 cross 3 or 4 cross 4 matrix. But imagine 1 lakh records here and you want to find out inverse. And then again, after multiplying it, X transpose X, then inverse. And then again X transpose, then multiplied. So this is also computationally very, very intensive. But you can directly get your thetas. So you have to see whether you are asked with a closed form solution or a gradient descent. Practically, gradient descent is more popular. Closed form is used when you have a limited data set, right? Because the computation becomes easy and you directly achieve your global minima points. That is what the beauty of this closed form solution is. You directly achieve your global minima points. So this is a little bit expansion of this, right? These are my points. This is my cost function. This is how I represent it, and these partial derivatives and all, right? I'm taking, and then Hermitian matrix. It is positive semi-definite, and this will also sort of come in this form. Consider the following: same training data. They have done this portion. They are calculating the errors, right? And directly you can solve these two equations now to come up to solve for theta 0 and theta 1, right? What I'll do is I'll make these you better use this simple thing, closed form solution, right? Because you know how to find out transpose, you know how to find out inverse, you know, for smaller data sets you can try it. Maybe for the same data set you can try this data set we have, right? This one. To try that particular thing and then see what are the results coming. It will directly give you the optimum results.
So for our data set, it will form a 2 cross 2 matrix.
Yeah, 2 cross 2, it will be very small. So imagine, say this is one thing that you have to do is you have to place 1 here normally, right? First column will be all ones. Then from here, the things start, right? Your first value. So obviously 2 cross 2, 1, 1, 1, 2, right? That is the value cycle. 1, 2, 3, 4. So 1, 1, 1, 3. That is your matrix. Theta 0 will be theta 0, theta 1 only, 2 bits. And then you start plugging these numbers here, right? Y is the value 2, 4 which you are having. So Y matrix is that. And you will get your theta 0, theta 1. Make sense? Now, for your exam, what you need to do? Prepare with gradient descent portion, right? This closed form, you try it, one or two questions, the same question you can try it directly. Naive Bayes classifier with Laplace correction, without Laplace. Simply Bayes theorem, using Bayes theorem, you make a prediction, then using Laplace, which we covered yesterday, right? So numerically, from numerical perspective, you try all these. SVM, I am not going to ask that optimization aspect and all, but general concept of SVM you should know. General concept of logistic regression you should know. Prior to this, whatever we have covered in terms of evaluation metrics, precision, recall, F1 score, confusion metrics, false positive, false negative, RMSE value, mean square, sum of square error, right? Then dealing with data quality issues, because real life data is very noisy, right? It needs to be treated before you feed it to the algorithm. There could be duplicate record, there could be negative values and all those things. So you should know what is machine learning, supervised machine learning, unsupervised, some examples, right? So these things you should study. If you find out any challenge, you can write an email to me. Though I will be traveling next week most of the time, but if I get time, right, I will try to answer that. You study. If you are facing any challenge with respect to any topic, you write an email to me. That will be better rather than sending messages on Teams or somewhere else. Does that make sense? Did you get something today? At least the gradient descent, we covered it in detail.
Yes, got it.
So better always come up with, I am okay with 5-10 students, but I should get the questions you are asking are valid questions. You should ask all these questions, right? Whenever we are dealing with, when we are doing our live sessions, right? It will keep you connected throughout the course. Anish, Ali, you used to be good, right? The moment I was teaching, right? The first 3 courses, I think I've taught you. But what has happened right now?
So there have been some work and personal commitments due to which I have not been able to attend regularly.
But at
With
least be
time, we have
be
more responsibility at the work also.
that you need to manage somehow, right? And at least stay connected with the course. Whatever the 2 hours we are spending, right? If you are there with focus, it will help you out to stay connected. Vasu is there most of the time. Shweta is also there, but she's keeping quiet. All right, fine. So I think these handwritten slides which I covered today, I think you need a reference to that, correct?
Yes, sir.
Yes, sir. And the fifth one as well.
Fifth one. I'll add it to the fifth one at the end and give it to you. Okay,
Okay.
for your
Okay,
reference.
sir.
If you don't get it by today end of the day, you please message me. Right? One of
Okay,
you
sir.
can message me. I will make it available. I have some other responsibility right now also, right? So once I'm done with that, I'll upload it.
Sure, sir.
That's why if I forget,
Yeah.
right, that's why I'm saying. So our schedule also goes like uh, we are working 7 days almost.
Okay.